Okay, so here we are, question 6 of VCAA's 2021 Specialist Maths Exam 2, Section B. All right, so what we have here in question 6, so it's a probability question, in sampling and stuff. All right, maximum load of a lift in a chocolate company's building is 1,000 kilos. The masses of the employees are normally distributed with a mean of 75 and a standard deviation of 8. On a particular morning, there are N employees about to use the lift. All right, so this question is about the lift and the masses. So each employee is an independent variable. So when we're working out the mean, this is each employee is 75 and 8, but when we're working out the expected value, we need to then take into account how many people that there are. And in your formula sheet on the third page, you'll see that they're random variables x and y, independent random variables x and y. The relationship's about the expectation value and the variance. And so what we know is that when we use that, the expectation value for the weight of n employees is 75 times n. The standard deviation for the weight of n employees will be 8 times the square root of n, whatever that n may be. All right, and so those relationships, as I said, formula sheet, page 3. Of course, remember the standard deviation is the square root of the variance. So you then need to work from there. All right, so what do we want? We want to know that the maximum possible value for n, for there to be less than one chance the list will exceed the maximum load. So the probability of the weight of the end exceeding its maximum load of 1,000, we want to be less than 0.01, 1%. All right, so what I'm going to do here is I'm going to use a standard value and then the conversion factor. So for my standard value, I'll look at the probability of Z being greater than Z1 to be less than 0.01. And so Z1, when you look that up on your calculator, in the inverse normal, and that's what you get. Now, my conversion factor I was talking about is Z is X minus the mean of n people over the standard deviation for the weight of n people. All right, so what have we got? We've got 2.3263 would be equal to, we're looking for 1,000 minus 75 n over 8 root n. And so then you get your calculator and solve for n, and you'll find that n is 12.45. All right, so you can't have 0.45 of a person, but we don't want to exceed the weight limit. So then, therefore, the maximum n is 12 employees or people. All right. So now we've got Claire. Claire, who is one of the employees, likes to have a hot drink after she exits the lift. The time taken for the drink to dispense has a mean of 2 minutes. Mean of 2 minutes. Standard deviation of 0.5 minutes. Times to dispense each successive are independent. All right, Claire's a meeting at 9, and at 8:52, she's fourth in the queue for a hot drink, assuming that waiting time is negligible and it takes 0.5 minutes to get from the drinks machine to the meeting. What is the probability that she gets there on time? Okay, so we want 4 drinks because Claire is fourth in line. She gets the 4th drink. So we want 4 drinks. So our expectation value of 4 drinks is simply 4 times the expectation value of 1 drink, which is 2, which is 8. Now our variance of 4 drinks excuse me, sorry, our variance of 4 drinks actually I've set it out in not the correct manner because they're independent, so I haven't really actually set that out correctly, so I'm sorry about that. What I should have done, but for the expectation value it doesn't matter, but what we've got for our variance though, because it does matter for the variance, because we've got drink plus drink plus drink plus drink, which is 4 lots of the variance of 1 drink. 1 plus 1 plus 1 was, so I should have actually set that out the same way. All right, now that's 4 times the variance of 1 drink, so standard deviation is 0.5, so it's 0.5 squared, which then of course is 1. So my standard deviation that I'm looking at of my drink plus drink plus drink plus drink then is the square root of that, which is 1. All right, so I should take more notice of my notes, because in my notes I did set it out as drink plus drink, because remember they're independent of each other. So it's this drink plus this drink plus this drink plus this drink, not 4 lots of the first drink. So I should have that, this lot here, written in the same way. That should be the expectation value of drink plus drink plus drink plus drink. All right, which ends up the same. All right, now, so what have I got? What we know then is she's got 8 minutes to get to her meeting, minus the 0.5 minutes for her to walk. So she's got 7.5 minutes. So what we want to know then is that the probability for her to walk, let's just call it D, or to get to the meeting, to get the drink and then the meeting, is less than 7.5, and then she gets there. All right, so we drag our calculator out, go to our statistics part there, and look up the normal distribution, and we find that 3085 is the probability, correct the 4 decimal places, she will get to her meeting on time. All right, next part of the question. She's a statistician for the company. Chocolate bars sold. Right, now we're on the chocolate bars. Sold with a mean of 60,000. Standard deviation of 5,000. To increase sales, company decides to run an advertising campaign. The mean daily sales from 14 randomly selected days was found to be 63,500. Claire's been asked to investigate whether advertising came as effective, so she decides to do a one-sided statistical test at the 1%. All right, null and alternative hypothesis. So null hypothesis is that the mean hasn't changed. All right, that's always our null hypothesis, that the mean hasn't changed. Our alternate hypothesis in this case is that it will have changed, and that's now different to 60,000. Now the question is, how is it different? Now here it says one-sided statistical analysis, and of the 1%, we won't worry too much about that. At the moment, we'll get to that for the next bit further down. But what was our sample that we took? Our sample was found to be 63,500. So our sample is bigger than what it originally was. So our one-sided test is now that the mean has actually increased, and it's now greater than 60,000. All right, so our p-value. So p-value that we're looking for. And to get our p-value, that would be the probability that the sample mean is greater than 63,500, because that's what we got, given that our mean is 60,000. And so our mean that we're using, of course, is 60,000. And our standard deviation would be 5,000, but we've got a sample here. So it's over root n, which is 14. And so we go to our calculator and go to our statistics part, and we're doing a test. And then when we put in that test, we find that our p-value is 0.0044. All right. So there's our p-value. Give it a reason. State whether there is any evidence for the success of the campaign. All right. So what we need to do is and the examiner's report said that you need to refer to the p-value. So our p-value is equal to 0.0044, and that is less than, we're talking about the 1% significance level, that's less than 0.01. So what we have is strong evidence the campaign's successful. All right, and so there's what you need to do, but you need to use the p-value, state the p-value as evidence. All right, so find the range of values for the mean daily sales of another 14 selected days that would lead to the null hypothesis being rejected. All right, so if it's rejected, then what we're looking at is the probability that the sample mean is greater than some value, given that the mean is 60,000, being less than 0.01. All right, so I know we want it to see when it is rejected. So what we're doing is the significance level I'm finding about the probability, because we're going to use the inverse cumulative. So we're wanting to go up to that. And so we want the mean being greater to be in that top part. Anyway, so if you look at your inverse norm and you use your right tail and you use your calculator, you'll find that this sample mean comes out to 63,108.713. All right, so that's the value where less than that, the probability is less than, so it's being rejected. So we want to accept it. So what we need is a mean value to be greater than or equal to, and that's when they talk about the range, greater than or equals the range. We want it to be greater than 63,100, and in this case we need to round it up. So we need to go bigger because it's bigger than the 0.7, 8.7, so bigger is the 9. All right. And the last one, the last says the advertising campaign has been successful and the mean sales now is 63,000. Statistical test is the 5% level. Find the probability null hypothesis would be incorrectly based on the sales of another 14, assuming the standard deviation is 5,003 decimal places. Sorry. So we're looking at doing the same kind of thing as our p-value as we've done above. So we're looking at the probability that the sample mean is greater than or equal to some value, given that the mean is 60,000. Now, why have I used 60,000? Because incorrectly accepted. So this is when we've accepted the null hypothesis, right? And we're looking at greater than in the top, in the 5%. So it's greater than 0.5. All right. And for that mean, that p-value to be greater than that, so we're looking for that mean, then that number is 62,198. All right, so it's been incorrectly accepted. So what we're looking at is that the probability of x bar, the mean, being less than or equal to that incorrect value, given that the mean is in actual fact 63,000. All right, and so when you do that, you get on your calculator 2741992, which is to 3 decimal places 274. All right, so for the to be incorrectly accepted, the mean would have to be greater than this. So that's why we've worked with the 6. The mean would have to be greater than that. And so what's the probability of the mean being greater than that, given the actual mean? And there it is there. All right, so there are some tricky bits in that last bit. That last question. I haven't actually shown the calculator process due to time. Our video would go to twice the length. But you can ask your teachers, etc. about that. All right, that's the last one in this particular exam. Make sure you look at the examiner's reports, refer to your teacher as well when you're doing your revisions.